welcome to Know Your Nonsense podcast. I'm Riley Judd.
And I'm Timothy Holloway.
I know about games, programming, and design.
I know about history, folklore, and food.
But neither of us know anything about yoga mats.
That is true. I'm not flexible enough for that. I can't do yoga.
Why?
I can't.
Flexible. But funny. Anyway, so today we are talking about binary. Yes, when 10 equals 2.
There are 10 people in this world. People who understand binary and people who don't.
I'm so happy you found that joke.
More than that, my dad has a shirt with that on it.
Really?
Yes.
Oh my goodness, that's glorious.
It's wonderful.
Yes, so Timothy is going to give us the lowdown on binary, and then I will fill in any holes, and then we're going to explore it a little further.
Right. All right. So yeah, here's binary. So all of you can get the joke that we just made about 10 people in the world. Yeah. So, binary. First thing, let's go over a little bit about the parts of binary. So if you've ever seen a movie where they have a hacker, you've likely seen a single code of binary at least once. Because it's all the 0's and 1's that go across the screens whenever some random hacker is like, I got to get past the mainframe, and they just show some B-roll of code.
So, yeah, it's just some binary. Which, disclaimer, I'm not a hacker, but I'm 99% sure that nobody hacks in binary, so...
That would be really impressive if
Do you know
they
how
did.
fast you would have to be typing 0's and 1's?
Extremely.
It'd be obnoxious.
And it wouldn't look like regular typing. It'd be those
just
two fingers chicken picking.
Attacking.
Yeah. But not the point. Binary is computer language, more or less. It's only in 0's and 1's. And parts of it are like this. Every 8 digits of binary is what we call a byte. Easy enough. A single digit of that byte is called a bit. And no fun thing, I'm not sure if they actually measure this, but 4 digits of a byte is called a nibble.
No, we use nibbles. Nibbles are
important. You use it? Okay, cool.
Because you can represent any of the normal numbers, 0 through 9.
Oh, right.
Nibbles.
I knew that. I'm stupid. Okay. Yeah, no. So, 4 digits of binary, 4 bits of a byte is a nibble.
Fun facts. But back to it.
But continuing on to a few words that you might have actually heard of. 1,000 bytes, 1,000 of those little 8-digit segments, that's a kilobyte, which you may have heard if you're old enough to know flash drives. A 32 kilobyte flash drive, that was popular.
Mm.
Yeah, makes sense.
Yeah.
Pain.
Just
make myself seem old.
I mean, yeah, everything nowadays is basically, at least storage-wise, is measured in gigabytes and terabytes, which
true.
We're getting to.
Yeah, that's actually what's next. Well, not quite, but 1,000 bytes is a kilobyte, 1,000 kilobytes is a megabyte, 1,000 megabytes is a gigabyte, and 1,000 gigabytes is a terabyte.
Yes.
That is a lot of data and a lot of information.
Yes.
So, as we mentioned, those digits of binary are either 0 or 1. It is what's called a base 2 system. So that's all you're going to deal with. You're only going to deal with 0's and 1's. And the reason that is because each one stands for a different thing. 1 is on, 0 is off.
Sometimes.
Right.
Yeah, it does depend on the system. Some, due to how it's switching from 0's to 1's, on might be easier represented with a 1. I mean, off might be easier represented with a 1 than a on. It's weird.
Right. But for ease of memory, I guess.
Yes.
1 is on, 0 is off. We'll stick with that for now. Now, binary can represent a bunch of different things. It can be used to represent numbers, 1 through 10. It has its own way of being shown in binary, thus the joke, 10 equals 2.
Yes.
But in addition to being able to represent numbers, or the value thereof,
yes,
you can also use binary to represent letters of the alphabet.
Yes, ASCII values.
Yeah, good stuff like that. So if you're ever looking at binary that is supposed to spell something out, let's say, which I don't think there's ever a reason where you'll have to do that unless you have a friend that's messing with you.
I mean, it was a good way of encrypting messages for a while. That's why Francis Bacon, which we'll get into a bit of the history later, but Francis Bacon, he took a binary number system and he was the one who invented how to represent characters with it. Mm-hmm. And so it's a fun way to code your messages, kind of like how people will use various and sundry ciphers and such,
yeah.
just for fun.
Ooh, ciphers would be a fun episode.
Yes.
Yeah.
Indeed, later.
Absolutely. That'd be amazing. But, so for instance, if you're looking at, somebody writing out their message in binary, if it has a 010 at the beginning, then that's a capital letter. Good to know. And if it's 011 at the very beginning, that's a lowercase. And after those prefixes, each digit will change in different ways. So remember, this is 8 digits long in total. After those 3 digits, you got 5 digits left. So starting with that digit furthermost left after those first 3, that only changes to a 1 from a 0 after the 16th letter of the alphabet. If you have binary and our normal alphabet side by side, that digit only changes after the 16th letter. That's the letter P, I believe. The one next to that, every 8 letters, that'll switch from 0 to 1, and then from 1 back to 0. Just like clockwork. After that, it's 4. After that, it's 2. And then the last one switches every single letter. Pretty simple. Hopefully simple. I hope I explained that well.
You're doing great. Just keep going. Great.
Okay.
Just keep going.
Yeah. But where did all this start? It actually started a long time ago.
Yes.
Back in ancient Egypt, believe it or not, which I did not go into very deeply.
Well, there's not much to go into.
Exactly, yeah. It's just reminiscent of a form of arithmetic that they had known as peasant math. Great. Why not?
Peasants math, running computers nowadays.
Yeah, it's so weird.
But
it's awesome.
Joke's on you, ancient pharaohs. Yeah. Take that.
Woohoo! But other than that, it also is reminiscent of the I Ching in China and some of the hexagram symbols that were in that book. That book is a book that was... how do I explain this? The book is traditionally said to be dictated by the Emperor Zifu, I believe. Zifu.
Okay.
And it's essentially just a bunch of, wise things and smart things. And one of them is a numbering system called hexagrams. And it actually allowed them to come up with some very supposedly prophetic and very well-written poetry. Yeah. Fun times. That actually becomes more important later on, too. With Gottfried Wilhelm Lebanese.
Yes.
Yes.
The
17th century mathematician and a polymath. Essentially just a really smart dude.
Co-inventor of calculus. You have him to thank for your calculus woes.
Yeah. Goodness gracious. Way to go, Lebanese.
Way to go.
Way to go.
I mean, you did benefit society, but also now we have to take classes in it. So
yeah.
It's a win-lose situation, I suppose.
Yeah. Fuji. Sorry. The Chinese I Ching, that was Fuji. That was the emperor.
And this is why we take good notes.
Yes, I had them. Just not all in the same spot.
Oh.
I'm working on it. I'm getting better. My tab problem does not only extend to computers.
This man has so many tabs open on his computers.
I do. It's fine. But Gottfried Leibniz, he proposed and developed our modern version of binary in one of his books, actually. And it was inspired by the I Ching's hexagrams. He was looking in particular at the selection known as the former heaven, and it apparently kind of matched up with some of his ideas that he already had, and he was just like, this is assurance that what I'm doing is important. He was already using 0's and 1's at this point to write out his binary. And to him, he was like, this is making my calculations so easy, I will have less error than standard division. Okay, dude, sure. But he found this to be so important, I thought this was amazing. He proposed that he got a silver medal from the Duke of Brunswick to commemorate this discovery.
Did he get one? I did
not find that.
Oh, no.
I didn't find if he actually got the medal, but I hope he did.
That's next level.
Yeah. The man, he knew his worth. Good for you, Leibniz. But that is kind of the start of modern binary, yes. I guess, in a way. Another jump ahead in that was with George Boole in the mid-1800s, British British mathematician, yeah?
I think so.
Boolean algebra and all that stuff.
Yes. Very important stuff.
But essentially, he devised forms of logic that encoded data with two terms. So that was your true false, your yes no, on off, 1 and 0, that kind of stuff. That was George Boole. And later, people realized, wait, George Boole's thoughts can be used in the form of things like switches. And that's where George Stibitz? George Stibitz? Is that how you say that?
I don't have him in my notes. Tell me what he does.
Well, he made the K-model computer. K-model being kitchen table. And essentially, it's made out of old tin cans, extra light bulbs and relays, and switches. And it processed the information in the same way that George Boole devised in his forms of logic. And it used the 0 and 1 binary method that Gottfried Lebanese came up with back in the 17th century. So yeah, it's just decades and decades of just building on each other's ideas and building on other mathematicians' crazy thoughts and studyings, and it all worked out. So that's fantastic. But then you start getting later models. These later models would at first be used with kind of relays that were devised for telephones. It was a bit slower. It was a bit clunky. But it was still getting better with each model. So after the telephone relays, they switched to vacuum tubes, which could turn power on and off much faster, making the speed of using the machine a lot faster. This is processing speeds that we still deal with today. You know, when too many people are on the Wi-Fi and everything just gets really slow. Kind of like that.
Kind of.
Not exactly.
It's fine.
It's an analogy. But with these faster processing speed, these computers could do more calculations. They were originally used to calculate ballistics on missiles during World War II. And as in sending out missiles, I believe.
Yeah, that sounds about right.
Yeah. But the problem was they were huge. As in sometimes 150 feet long, multiple tons in weight. Instead of a monitor, there were huge banks of flashing lights that would be flashing different lines and patterns and fun stuff like that.
Yes.
But they also used punch cards, which were just little paper cards that people would either by hand or with the aid of a computer. They would punch out where they wanted switches to turn on or off. And that was, again, using that 8-bit segment form of binary. From the punch cards, they moved to using magnetic tape, still using that same code. Still no monitors at this point, just lights, tape, and paper. And it would sometimes spit out paper back at you to tell you the results and to keep programs. You would punch out the same holes that you needed, and then you could file that away wherever, and then pull it back out and have the computer read it again. People started at this point seeing more applications for these binary processes as they got faster, like counting votes in the 1952 presidential election. It was a huge test that, if it had gone wrong, probably would have halted a lot of the operations that were going on.
Yeah.
But it didn't. It went right. It went very right, and Eisenhower won in a landslide election. But...
Or did it? Conspiracy!
Let's not go
We're not a conspiracy podcast, so
no,
sorry.
We're not.
Just wanted to make the joke.
If you want a conspiracy podcast, go find them. They're out there.
Yes.
But binary started to get used in business, in commerce, trade, you name it. People started realizing a need for it. And it is continually used still, despite growing innovations. They never phased it out because this is just it's what works.
If it ain't broke, don't fix it.
Exactly. So even our modern computers, they still use binary. So I'm going to kind of go through a very, very simplified layman's way of understanding how computers use binary. We'll see how this goes.
I'm very excited.
Yeah, me too. Okay. Every keystroke that you make on a keyboard, it sends a signal.
Oh, you starting there?
Yeah, I'm starting there.
All right.
Where should I start?
I don't know, but that was not the place I was expecting. So okay. Keep going. Carry on.
So every keystroke sends a signal in binary. More or less, it's telling I guess that would be applications in the computer, because that's what's reading the code, what to turn on and off. It's very simplified,
going.
remember.
Keep going.
What to turn on and off, and that binary is turned into what is called Ascii code, and that is then telling the rest of the computer what to show as output. The same process is with files that you're trying to access. Each file is stored as a number, the number is translated into binary, and it tells the computer what to produce. Now, this can be any sort of file. It can be a Word file, it can be an audio file, like a podcast. It can be a picture file. For instance, photos, they're divided into pixels, a bunch of pixels in many ways. In most ways now. Because pixel count is so large nowadays.
I mean, yes. But then we get into vector graphics. But that's another episode.
That's definitely another episode. But each pixel gets its color via a number associated with it and a binary correspondent with that number. So if you imagine 3 pixels right next to each other, pixel A, that number that is associated with pixel A is number 1. Let's say that corresponds with a 1 in binary. Because it does. You know, that's a whole value translation of what we know as 1 into binary. It's 1.
I think I'm going to have to cut you off
there. Oh, great.
This is not quite how the pictures work. It's a lot more complicated than that. But I appreciate the effort.
Yeah, of course. No problem.
So sorry to derail you, but we're going to have to cut that one off.
That's fair. Will you cover that later?
I can cover some of the basics. It's been a while.
Okay, that works. So yeah, we'll have to hear more about imagery later.
Yes.
In that case, I'm not even going to try and get into audio.
No, you can try to get into because I can't refute you. So I mean, our audience could. So give them something to refute.
All I know for audio is that it's real complicated.
Yes,
for one,
a lot. It's a lot.
And each MP3 file has what's called an ASCII representation. That ASCII code, it's another form of code that corresponds with binary. It corresponds with other things the computer can read. And that is then read and translated to sound by an MP3 application, more or less. It's really complicated. Too much to get into in this episode. The baseline thing to know here is that the applications. That's what's reading the code. That's what's doing the work. That's what's translating the binary into what we see and feel and experience. That's translating the binary to the output.
Kind of, yes.
In the most simplified way.
Okay, you do need to bring up the CPU, or the central processing unit, in your computer. It is what's actually, at least, if we want to go back to the keystroke, then it's going to be what takes some of those binary representations and tells the various other parts of the computer what needs to happen based on them. So with things like MP3, yes, they are applications that are built in. Well, if they're built into the computer, then they're kind of built into the central processing unit, most likely. But whatever. So yes, there is a program that's doing it, but also it is important to give credit to the ever-important CPU. That's why you take care of your CPUs, people, because it's running essentially your entire computer. I mean, it's not even essentially. It's literally what it's the heart. It's what's making your computer tick. So
yeah, no, that's fair. I just didn't go into it because
I just wanted to bring it up. Got
that's a good thing to do. Yeah, definitely take care of the CPU because that thing.
Take care of your computers, folks. Give them a good dusting.
Give them a good pat on the monitor.
No, don't give them a pat on the monitor. Why would you say that?
It was supposed to be equivalent to pat on the back, but I realized I don't know what the back of a computer would be in that case.
The back of a computer. We're moving on.
Yeah, we're moving on. It's fine. So, one of the last things I'll cover is programming languages, which I will not dive deep into.
No.
But that's typically what people think of when they're thinking about programming. I mean,
that's what people program in nowadays.
Exactly, yeah. Because they're not writing out binary.
No, because you can go and write binary It's the worst. You don't want to.
It takes a long time.
Yes, there's a reason, like, you just don't do it anymore. It's because people much further prior made these advancements so we didn't have to do it anymore.
Right. And so here's how those work with binary. So programmers, they'll write in different programming languages like Java, Python, C++, if you've heard of any of those.
Yes.
Then whatever they write in that language, that is then passed into a file in a sort of text form. Then, simplified, remember.
You're shooting yourself in the foot, but keep going.
All right. That file then goes through what's called a compiler. The compiler translates that source language to what's called object code in the form of binary. That is the program itself. It can be modified, but in order for it to actually run the modifications, it has to be recompiled. So yeah, that's programming language. Other than that, that's most of what I have.
Okay.
Most all of what I have.
Well then first, I gotta make an addendum to the languages.
Yes, please do. I knew that was really condensed.
You listed, Java, Python, and C++?
Yeah.
These are not created equal, my friend.
Oh, no, for sure. I wasn't trying to imply they were.
No, but so with the compiler part.
Right, okay.
So C++ is a good example of this. That is a compiled language. So what's happening is what you said. When you are ready for your program to run, you hit the compile button, and that sends your text file to the compiler, and it does spit out the OBJ file, which it contains all the binary that can be run.
Okay.
However, when it comes to things like Python and Java, don't quote me on Java if I'm a failure of a computer science. We're just going to go with Python because I know Python fits this description. That is an interpreted language, which is different from a compiled language. And it is not translated to the whole file is not translated to binary before you run it. It changes it to binary on the fly. So as the program is running, as it's going down those lines of text, that's when it's changing it to binary.
Interesting. Okay.
Yes. So with a compiled language, they tend to be a lot faster because you don't have to do these translations in real time. They've all been done before. That's why if you have a program that's millions of lines of code, it can take a long time to compile, but then it will run just fine because all of it's been compiled. And it is able to catch errors a lot easier because it's gone through the entire file, and if there's an error, it can say, there was an error. It was here. Meanwhile, in Python, it's just going to keep going and eventually hit something and be like, I don't know, man, something went wrong. It could be here. It could be somewhere else. I don't really know because I've been reading this broken script as we've been going. So, but it's important to note that when it's translated into binary. So, compiled languages like C++, all at the beginning. Interpreted language, or there also are pseudocode languages, which I think Python is technically. These are translated into binary, but it's pseudocode, which is then interpreted by an interpreter. So an interpreter is what's going through the text of an interpreted language and changing it into the binary that can be run. So this is sort of a middleman with pseudocode languages. You're turning it into binary, which can be read faster, but it's still not the runnable code version of the binary, if that makes sense.
I think so.
Cool.
Yes. Okay, cool.
Yes. And then
is Python the one you really don't like?
No, that's Java. I don't like Java, and I'm going to get destroyed for saying that, but I don't like it. It's just not my fave.
Fair enough.
Yeah, so if it's your fave, I'm sorry. If it's not your fave, thank you for being smart. No, I'm just kidding. But I do want to get into a little bit more about the binary systems, the base 2. I was hoping
I did
you
not
would
cover base 2
No.
that much.
So this really relates to how you can think of it in terms of the decimal system that we use. So the system that we use is known as the Deanery System, or the Deanery, I think it's Deanery System. So it has a base of 10. So we have the digits 0 through 9.
Right.
And then whenever you reach the end of that, so take the 1's, so 0 through 9, you have a single position, and you're going to cycle through those numbers until you hit 9. Well, if you add another, well, you're out of digits. So you add another position to the front, that will become the first number. So it's essentially going from 0, which is not written, to 1, and then the original position goes back to 0. That's how you get 10. So you just keep doing this. So if you go back up to 19 and it rolls over, then you change the 1 to a 2, and the first position goes back down to 0.
Right.
Binary is just that, but instead of going 0 through 9, you go 0, 1, and then you're done. So when you hit 2, you have to add a new position, and its count goes up from 0 to 1, and the original one goes back down to 0. So that's why 1, 0, or 10, equals 2. Because it is... So if... we say the powers, so every position in the Deanery system, in the decimal system, is a power of 10. So 10, 100, 1,000, 10,000. Well, everything in the binary system is a power of 2. So you are going to go, the 1's place, and then 2, 4, 8, 16, 32, 64, and so on and so forth.
Yeah.
And you just keep rolling over just like you would do in a normal number system, but you just don't ever... Your only two digits you're working with are a 0 and a 1. And because those are easily represented in physical states, like on, off, or, up, down, open, closed, that's why it's so beautiful when it comes to computing, is because we can physically represent those things. And that's why it's never changed. We have actually made ternary computers. So those are ones, instead of 2 options, there's 3. They are much faster. They are also infinitely more complex. It's so much easier to just have a yes-no than it is to have a yes-no kind of.
Yeah, no, that'd be really confusing.
Yes, so that's why we have stuck with the binary system for all this time. And going back to the character system, I didn't like his explanation.
Yeah, no, that was a very strange explanation.
You weren't far off. So when it comes to binary, different binary systems will use a different amount of bits, or the single positions, to represent things. So when it comes to ASCII characters, they're usually represented with 8 digits. So 8 bits, a byte. And depending on what that number is, that's how you get your character. I don't remember what the system you're describing is called. I'm a failure of a computer scientist, but what you're describing is the more advanced version of the ASCII chart, if that makes any sense. Advanced. It allows for more options.
Gotcha.
Because when you have 8, you are limited to 255 characters. Because if all 8 of those are a 1, that equals 255.
Right.
So the one you're describing allows for a lot more, because we've gone past that power of 2. So, 256, that power, square that. And that's a lot more positions.
That is, yeah.
Yes. So, but when he's describing how every couple of numbers they change, that has to do with just how the binary system works. So how you mentioned that the last one, the far right one, changes on every character.
Right.
Because that is essentially your 1 counter.
Yeah.
So when you go from, 0 to 1, well, you're going from 0 to 1. When you go from 1 to 2, well, it's going back to 0. So it's always flipping. And then all the others that you were describing were the flips from their powers of 2, if that makes any sense.
It does, yeah.
Yes.
Yeah.
So overall, a pretty good job. I mean, this is a very complicated topic.
It was rough.
Yes.
It was fun, though.
Yes.
It was very fun to learn about.
It's one of those things that it's fun to know, but also in computer science classes, they're going to tell you, look, we want you to appreciate this, but you're never actually going to use it. Like, I don't think there's ever going to be a scenario in my programming career where I have to code in binary. I pray that never happens. But it's fun to know. It's fun, exciting stuff.
Yeah. And I feel like once you get to a certain point in it, I feel like it would be easier to understand if you think of it in the context of what binary is, not in trying to relate it to what you already know in the Deanery System. Does that make sense?
Yes. I mean, it's literally another language translation. When I took machine assembly and architecture, that's the class where they teach you binary. I was actually pretty good at reading binary. Like, I could look at a 8-digit binary number and go, oh, and that's what it is. Now, I couldn't give you the Ascii for what it is. I mean, a couple of the very common ones, like I knew the vowels pretty well because it's just a pattern, and once you recognize the pattern, got it down. So if we wanted to talk about digits, so the standard numbers for 0 through 9, 10, your standard numbers, those can be represented with a nibble. So 4 characters, and 1010 is 10, and I still recognize that one because it's 2 10s. So I think that's kind of funny.
Easy.
Yes. So I think that's about what we got for the summary. So we will take a short little break, and then we will come back and discuss a little further. So
yes, we will.
Yes, stay tuned.
Stick around. Hey, Riley.
Hey, Timothy.
Do you remember when we first started this podcast and we had no idea how to get started or do anything with it?
Oh, you mean like how we're still kind of operating?
Almost. Except back then, we had no idea what podcast service to use or how to even step into the world of podcasting.
No, we did not. I knew nothing about starting a podcast.
Well, then let me just say how glad I am that we found Anchor.
Yes, it has so many wonderful things about it that have helped us break into the podcasting gig.
Amen.
The first little bit is that it is free. That was one of our biggest concerns. There is no money required to host a podcast on Anchor FM.
Right, you can get your name out there. And another great thing that they have are editing tools for you to use on your phone, on your PC. You don't have to go out and spend money on an editing software for you to edit your audio. In addition to those free editing tools, they have a whole library of different music and sound effects that you can choose to add to your podcast, all for free.
That's a lot of good free stuff.
It is.
Yes. Another great thing is that they distribute your podcast to a bunch of other podcast hosting sites. So things like Spotify, Apple Podcasts, Google Podcasts, you name it, they probably send your podcast there. So it makes it more accessible than ever to all the people that you want to reach.
And once you get on your feet in the podcasting world, they make it super easy to find sponsorships and get paid.
Yes. So if you are looking to start a podcast, break into the podcasting industry, go ahead and download the free Anchor app or go to anchor.fm to get started.
Do it. You won't regret it.
You will not. And we are back, folks.
Hello, did you miss us?
Because we missed you. So, back to the conversation.
Right, about binary.
Yes, about binary. So, Timothy.
Yes, Riley.
What did you find most surprising, the most wild about binary?
How freaking old it is.
Oh, yes.
Holy cow. Like, I had no idea. Going into this not knowing hardly anything, I figured, binary, it's probably early computer stuff, 40s, 30s.
Nope.
17th century.
Yeah, you'd be surprised how much stuff in the computer science world is built on century-old information.
Really, though?
They just didn't quite have the technology to make it happen in the computerized fashion that we do today.
I know, right? But, even just knowing that the man was already like, oh yeah, it's a 0's and 1's, base 2 system for calculations and, all this crap.
Like we mentioned, so you had Gottfried who made the calculating system, but then you had Francis Bacon, as we mentioned, who was making the character representation system. So for any of you who didn't quite pick up on it, when we were saying ASCII values, ASCII characters, those are just text characters. So think letters, numbers, symbols represented by a byte. And that was Francis Bacon, who he was coming up with that for encoding messages before Gottfried even started his calculations in binary.
Yeah, so it's even older than anything that I talked about. Well, unless you count the Egyptians.
I know,
and the I Ching, but that's
it's
technically not the same thing.
No, it's technically not, but it was still a two-number counting system.
Exactly.
Which is essentially what binary
the
is.
The Egyptians were.
Well, yes.
I think the I Ching was 7 numbers.
Yeah.
It's technically like 7 layers. It's super cool. Later episode, maybe.
Well, I mean, that is worth bringing up because you can have a number system based on any number. So my professor at my college, Dr. Baber, he liked to prove this point with his base -3 system.
Why?
Because you can.
Okay,
it was literally...
That's fair, but why?
Oh, it was so fascinating. He wrote it on the board and counted in it, and all of us are just sitting there flabbergasted because why would you ever make a number system that goes positive, negative, positive, negative? Because when you go by powers of negative numbers, that's what happens. You know, take it, let's say we were doing base -2 just for because everybody can do 2s. So you would go -2, 1, -2, 4, -8, 16, -32.
I don't like this.
But you can. You can have a number system. If any of you...
Why would you want to?
For the meme.
Carry on.
Yeah. So if any of you are really feeling spicy and have too much time on your hands, make yourself a number system. Just base it on whatever number you feel like and have a great time. And then let us know what number you chose.
Yes, please share with us if you decide to make your own number system based off of this. That is amazing. Technically speaking, you don't even necessarily have to keep it in numbers. The shorthand for binary, which is hexadecimal, it is base 16. Well, you don't have enough numbers to cover that. Yeah. So it goes 0 through 9 and then A through F. Yeah, I purposefully did not go into hexadecimal at all because that was a lot.
Yeah.
Although it did save Mark Watney's life in the movie The Martian.
Yes, it did.
That was amazing. I love that movie so much.
That's a great movie.
It's fantastic.
It's a good science movie.
It really is. Makes me want to go to space even more. Is that weird?
No, not really.
Oh,
I mean, I don't feel it. I'm if we ever perfect space travel, I'm staying right here on Big Blue and not moving.
Fair.
So
that's fair. But Elon, look for me.
No. All right. So moving on.
Yes, moving on. Riley, tell me, what did you think you knew and was maybe wrong about, or what caught you off guard again? Maybe.
Just a lot of the details, because I've had a class over this. I've had a class over all of this. I should know a lot of this stuff, and some of the details just got mixed up in my brain. Like, I thought Francis Bacon was the one who invented binary, and, I Googled that question because that's a great place to start. Who invented binary? And I got Gottfried, and I was, I was wrong. But then, of course,
Gottfried Lebanese.
Then you have to, why do I think it's Francis Bacon? And he did work with binary.
Right.
He just didn't make the binary calculation system, which is how binary code works. So.
Right.
Yes. And
both of their contributions to that concept of binary are both very important.
Yes, they were both very influential in binary coding that we use today in computers, but I just had a few of the details mixed up, so I'm sadly a bit of an unreliable narrator when it comes to the actual details, so if we've gotten anything wrong, I apologize that I'm a failure of a computer scientist. I will do better next time.
Just let us know in our emails.
Yes, just let us know what we failed at.
Right.
Yes. So, Timothy, what did you want to learn more about but couldn't find?
Okay, I wanted... It wasn't that I couldn't find it, probably.
Yes, but what did you want to...
I could have found it.
Yes.
I wanted to know and learn how to do binary calculations.
No, you don't.
Yes, I do.
No.
One of the first things I read whenever I looked up, who created binary? Why did they create binary? It's, Gottfried, Lebanese, and he's like, this will make my calculations so easy and so much less error. Errored?
Error. It makes so much more error-free? I don't know.
I guess, yeah. And so I started thinking, it's like, this is still when I know little to nothing about binary. Still don't. I know a lot more than I did, and I'm very happy with that. But I started looking at it, and I was like, I didn't know you could do calculations with binary. How does that work? I'll come back to this. And then I got caught up trying to understand how pixels happened and how audio... Oh, we didn't cover that.
I didn't. Okay, so pixels. Yes. So you're not entirely wrong when it came to that. There's just a lot more information being stuffed in than just, this is a pixel, here is a number. Because a pixel will most likely... If you were going real basic, it's got to have a position, it's got to have and then it's got to have an RGB value, so a red, green, and a blue value. Each of those has to be represented by its own number.
Oh my.
And so it's more than just a single binary, like a single byte. It's more than that. Which actually, fun art fact, if you ever... open up any MS Paint or something, and it lets you select your colors, and it's being done in RGB or I believe CYMK as well. Yeah, the values go from 0 to 255 because that can be represented in a byte.
Okay, I get that. Okay,
yes, that's why that's how the color spectrum works when it comes to computers. Fun stuff. Yeah, but. Back to it. So you wanted to know more about the binary calculations.
Yes, I did. Because the first thing I read about this stuff is oh yeah, it makes my calculations more error-free than if I'm using standard division, which I don't know if he was trying to say standard division needs changing, or if he was trying to say that he's bad at standard division, or it's just a flawed system. Yeah. It doesn't have as much... It does have trial and error in standard division. Maybe that's what he was talking about.
Yeah.
But either way, I'm like, okay, well, yeah. I want to learn about this. I want to find out what this means. And then I didn't get around to it until very late in the game after I'd already fried my noggin trying to learn everything else.
Yeah, well, I mean, there is a good chance that you would have just been chasing the wrong rabbit holes if you did try to dive into it, because you would have gotten a lot of George Boole's work on Boolean algebra, because that is... not to say more important, but it's more used when it comes to computers and calculations in binary. It's more common than if you're trying to do calculus calculations. So adding, subtracting, multiplying, dividing with binary. Which Boolean algebra is its own complete different beast. So for those of you who don't know, Boolean is essentially a term for true or false. In layman's terms, it's just it's a word for a binary choice. So, a yes, a no, an on, and off, a true, a false. So whenever you're doing Boolean algebra, instead of using things, and again, this is fuzzy memory, but I'm pretty sure I got this right, is instead of having things like this binary number divided by this binary number, you have this binary number or this binary number. But instead of saying I choose this one or I choose this one, you're doing it the way you would say, multiply or divide. You're taking each one of those bits, one of those little pieces in the binary number, and you are checking one or the other. It's a really complicated mess.
We'll just
move on.
Mention possibly having an episode about that, and then maybe never getting around to it.
Maybe never get around to it.
I still want to learn about it, but yeah, not for this episode.
But it's okay. That being said, it might be tricky to find nowadays what Gottfried was looking into when he was talking about calculations, because George Boole's work is so prevalent nowadays in what we do. It's one of the foundations on how your computer makes any calculation that it needs to make.
Okay. Well, gotcha.
Yes.
That makes sense. What about you? Did you have anything that you wanted to learn more about or wanted to find?
I wanted to dive a little deeper into punch card computers. Because once I read that punch cards were essentially just binary cards, it just made so much sense. I had never really considered how computers ran on punch cards. It is just one of those things that you just accepted. Like, okay, old computers run on punch cards. Cool. And then they weren't. But once it's explained, that's a binary thing. There's either a whole or there is not. That is a binary 2-item system.
Right, yeah.
It just makes so much sense. And that just got me so much more interested. Like, so you would give it the punch card and then it would do what? Like, how did it read the punch card? Where did that information get stored? What was performing the Boolean algebra to spit out results?
Right.
It was just very, very interesting to me. So I wish I had dived a little more into it, but sadly I did not.
I wish I had too, honestly. That's super interesting. It makes me think of those little, like, windy instruments where you punch out the notes on the piece of long strip of paper. And
it's the same system, essentially. It's also a binary system. There are more than just computers that run on these things. You had old-fashioned looms that would run on a similar system, and like Timothy said, the music boxes, they would run on a similar system. So binary has more than just computing uses. Yeah.
It's more than just on your desktop or laptop or phone, I guess.
Literally, if there's something that's running on any sort of like digital device, it's running on binary.
Yeah, it's wild, man.
Nowadays, I don't really know what this would relate to in our original like first half, but nowadays all of the options, so the ons and offs, how that works electric wise is we have little tiny things called transistors, which they take 2 inputs and then they have 1 output, and depending on the type of transistor you use, you're going to get a different result. And so that's how it makes those binary choices, and it sends the electric currents on. And that's why with electricity, that's just the small physical way that we've determined to represent something binary, because it can be either there is electricity or there is not electricity. That is a on-off, yes-no binary option.
For sure. Still around us every day.
Yes.
Like we talked about power switches.
Oh, yeah.
The symbol, the little circle with the line through it, and also the other switches with the line on one side and the circle on the other.
Yes.
1's and 0's.
1's and 0's, ons, offs. Like, that's what those symbols represent. So if you are listening in on your computer and you have that little icon still, a lot of buttons have gotten kind of small, so they may or may not have them. But that circle with the line at the top, that is the idea, a 1 or a 0. Yeah. And same on your light switches. Some light switches on the top, there will be, a
just
0.
A line.
Yeah, just a line or a circle. And that's where it comes from.
Binary.
Binary, folks. So
everything we got for that?
I think that's about all we got. I think that about wraps us up.
All right. Well, let us know if we got anything wrong.
Yes, which complicated topic, very likely.
Yes, please. We hope we made it easier for you to understand parts of it, though. So
yes, at the very least, you now understand a little more about the wizard behind the curtain that is binary.
Exactly. But let us know what you thought at kynpodcast@gmail.com.
Yes, and you can also contact us and follow us on any of our social medias: Instagram, Facebook, Twitter, all the works, YouTube. Pinterest, yes, it's all KYN Podcast, so you can find us real easy.
Don't forget to check out our new Patreon that we just set up.
Yes.
If you want to consider becoming a patron and supporting this podcast, we would love it, and we love it anyway because you're listening to us, honestly.
Yes, indeed. But with that Patreon account, you will get exclusive perks, such as our extra episodes of Ryle's Reviews and Tim's Tales. So if you wish to tune into those, then go give us a look on Patreon, and then you can also check out our Teespring account, where you can get merch of our lovely KYN podcast designs.
Exactly. Our graphics made by Riley in-house.
Yes.
Woohoo. Go check those out and take a look and get yourself some KYN merch.
Yes. So now we're on to the hint for our next off-brand episode.
Exactly. Next big episode.
Yes. So the hint is life has its ups and downs,
but we will always put our money where our mouth is.
Yes.
Indeed.
That is the hint. We hope you all have a great time pondering agonizing over what it could possibly be.
Yes. Let us know if you figured it out or if you have an idea.
Yes.
We won't tell you if you're right until the day we release, I guess.
Of course.
Hey.
Yeah, you just have to sit in suspense. But it is worth noting that this episode, this off-brand episode, will be happening 2 weeks from now because we will be having a nice breather episode.
Right, just a fun time.
Yes, a fun time to be had by all.
Yeah.
So tune in next week for that breather episode, and then tune in the week after that for our off-brand.
Figure out that hint. We're giving you plenty of time.
Plenty of time, folks. So
for now, have a great day.
The greatest day.
And we never sign off like this. What is happening?
We've never made an official sign off because they're all trained. Bye!